So let's start officially. Welcome to the RGI hosted webinar, The Advantages of Electrification for Decarbonization. This webinar will be held by Saul Griffith, who you can already see on, from European perspective, the other side of the planet very early in the morning. My name is Antina Sander. I am the Deputy CEO of RGI and going to moderate this webinar. For those who do not know RGI, we had a slide, but for technology reasons, we don't show it right now. We are a membership organization where since 10 years, TSOs and NGOs collaborate in the context of how do we get this energy system, the grid build that we need for the energy transition in respect of nature and societal concerns that encompasses to not build anything more in terms of infrastructure than what is indeed needed for this energy transition, which is of course the direct linkage to the talk that we are listening to today. Our presenter, Saul Griffith, is, and Saul, we haven't met other than on this channel half an hour ago. So if I say something that you not agree with, please just correct me. But I heard you are the CEO, founder, and a principal scientist at an organization called Other Lab, which is an incubator accelerator for its own ideas in the sphere of renewable energy and robotics. Other Lab has spun off so far 12 companies, and your main focus is clean energy and the zero carbon economy. You hold a PhD from MIT and a couple of degrees in material science and mechanical engineering, I found out, and you also have a solid track record in winning awards for inventions that you have made. You have received this year the Thalberg Eliasson Global Leadership Prize, which is an award given to men and women that demonstrate imaginative, system-based, risk-taking, and ethical leadership behavior to tackle challenges of the 21st century. And this is where you've actually met the RGI founder, Antonella Battaglini, who has been in this group of award winners a couple of years ago. And through this, Antonella has heard you talk about the work you do in energy system modeling for the US, based on very high resolution data and starting from the demand side. And there she told me going down actually to the single use level. And it's about this work and what you have found out that we are going to hear about in this talk. I will leave what this is to you. On the housekeeping, we plan for roughly an hour of presentation, but that depends a bit on how many questions come in. Dear participants, you are invited to ask questions via the Q&A function at any time. What I will do then is I will hold up the sophisticated signer so that Saul can see that there is a question, and he will pause at the right point in time when it's convenient, and then I will read out the question because we are able to see it here, but Saul will not be able to see it as far as I've understood. So it may be a bit with some time gaps in between, but we try the best. So feel free to ask your questions anytime you want. Raise your questions via the Q&A function of this application. Now we can hear someone talking. Be the case? Exactly. We are not able to hear you. Yeah.
I haven't said anything yet, so can you hear me?
Can hear you. We should be. And hopefully everyone else can. Interesting. Can you type in the chat? Yes, we can hear you.
How do I say that?
Yeah, I get a chat saying yes. Awesome. We assume everyone can hear us, and the floor is yours. The stage is yours.
Good morning. I'm noticing, I hope you can hear me, because given my beard, I don't think anyone could read my lips, which might be a problem. Thank you, Antina, for the introduction. Maybe before we start on energy, I'll give you a little more sense of what we do. So what the lab actually develops new technologies. We invented an offshore wind energy technology that was in fact just deployed with Google and Shell in Norway. We founded a company called Sunfolding that does industrial solar tracking, and we're just at this point deploying gigawatts of that each week. We have an air conditioning company focused on the 15% of emissions from air conditioning. We have technologies there that can potentially decarbonize and remove the emissions entirely from air conditioning. And so by day, what I do is I work on those types of technologies. New technologies either for efficiency or for generation for decarbonizing. Because of that, I've had a long-standing interest in energy data. So why do we think we know what we know about energy? And today, I'm going to be talking a little bit as a lead into electrification, the history of what we know about energy consumption. And it will be all US data, but because the US started measuring these things first, it's an interesting way to talk about what the world thinks it knows about how we consume and use energy. And I think that historical conversation also informs a couple of the blind spots that we have when we contemplate how would you decarbonize an economy. Happy to take questions. I think Antina's going to hold up a Russian doll when when anyone asks a question. I enjoy doing the questions in real time. I have 30 or 40 presentations on this computer, all of which could be relevant for this audience. So if you have a detailed or question, I probably can bring something up with some fumbling that will talk to that question. Just for some historical context, this is Silent Spring. I think it's probably the best environmentalist book ever written, because it not only highlights a very important environmental problem, but it was written beautifully and poetically. That book was written in 1962 and had a huge influence on the environmental movement, and in some ways started the chain of events that led to the way we collect energy data. In 1965, 3 years after that publication, there was, and largely influenced, in fact, by the issues that Rachel Carson had brought up, the president of the US, Lyndon Johnson at that time, commissioned this study on restoring the quality of our environment. And this is an interesting document historically, because if you look at the contents page, maybe Antina can nod if she is seeing the same thing that I'm seeing. Fantastic. And you can see in the sub-panel report Y4 on page 111, atmospheric carbon dioxide. And this was in fact the first, and this is the beginning of that. It's maybe worth going back and reading this after this. My slides will be made available to everyone, I'm sure. But this was the first report to land on a president's office in the United States that discussed quite concisely the problem of carbon dioxide. And you could reasonably say that the president of the US in 1965 had a better grasp of the problem of carbon dioxide than the president in 2020 or 2019, which is a problem. 1971 came around, and this was the beginning of America's awareness that they had an energy problem. That landed on Richard Nixon's desk, and it was still arising out of the questions of the environmental consequences of energy production. So this is before the energy embargoes of the 70s, but this was more from the Rachel Carson and concern for the environment. And this, we had already we were already aware of the air pollution issues, for example, in Los Angeles from cars, and the air pollution issues because of burning coal. And so even Richard Nixon, who we don't hold up as a stalwart of environmentalism, was calling for a sufficient supply of clean energy, as you can see. Then 1973 happened. This is the scene at the oil pump in America during the initial Arab embargo, oil embargo, which was a problem again that landed on the desk of Richard Nixon. At that time in 1973, the United States had no EPA, they had no Department of Energy, they had no Energy Information Administration. And so when the president was concerned about the United States supply of energy, the committee that they asked to have a look at this was actually the Joint Committee on Atomic Energy, which was a committee that was tasked post-World War II in America of looking for the peaceful applications of atomic energy. And this is actually the committee that made the statement that nuclear power will be too cheap to meter. The task given to them in 1973 was develop energy displays and energy visualization tools that could enable members of Congress to understand in less than an hour what the challenge for the American energy supply was. This was the book that ultimately was published that was the answer to that question, Understanding the National Energy Dilemma. Briefly jumping back 100 years, but I'll come back. Many of you may have heard of, or hopefully have all looked at, Sankey energy flow diagrams. If you are interested in energy and decarbonisation, I imagine you have. The first Sankey diagram it's often attributed to Captain Matthew Henry Phineas Ryle Sankey, who was in the British Navy, and he drew this diagram, which is a Sankey efficiency or energy flow diagram through the boiler in his steamship. But we've since realized that perhaps a little bit earlier, this Sankey diagram by Maynard actually shows the flow of Napoleon's soldiers as they marched into Russia. So there's an interesting diagram. It starts on the left. So the width of that brown arrow that starts on the left is the number of soldiers in the army. And you can see as he progresses into Russia, the army gets whittled down and whittled down and whittled down until eventually they get to Moscow with about a quarter of their soldiers, and then they lose another 3/4 of that as they retreat. So it's a fairly dark and sinister Sankey diagram, but that's actually where we first developed this visual language of showing flows of materials or people or energy systems that are conservative in a Sankey type diagram. This was in fact published almost in parallel to the National Energy Dilemma in Scientific American. Energy in 1973 in America was on everybody's mind because of fuel restrictions and heating restrictions. I just add this here in some respects to show how far we haven't come. Anyway, here was the National Energy Dilemma. They showed the energy consumption as a very simple Sankey diagram. Sorry, here we go. Every year, and you can see as I flip through these slides, basically the first one, I think, if we go back to this, I think it was 1950, 1960, 1970, and then they predicted this is what they needed by 2000, or no, 1980 and 2000. And you can see they actually intended to show that because this was increasing the energy consumption and demand so quickly for the United States, because they were the Atomic Energy Committee, that the only way to solve this problem, because they were projecting, I think, if we were using their projections, America would be using 5 times as much energy today as it actually is. So they projected that we could only do that with atomic energy. That work ultimately led to Nixon setting in motion the creation of the Department of Energy and the Energy Information Administration. Incidentally, he also began the EPA, and this is the first energy flow diagram that was published by Lawrence Livermore Laboratory in partnership with the Energy Information Administration in 1976. So this was the first time, and since this moment, America has been publishing this energy flow diagram every year. Maybe just to make sure that everyone's up to speed here, you read these things from left to right. So on the left-hand side, this is called the primary energy input. That's the cubic feet of natural gas or cubic meters. This is the tons of coal, barrels of oil, and how they flow through, and we made some fairly arbitrary decisions in 1976 on how we would draw these diagrams, how it would flow into electricity generation, residential and commercial, industrial, and transportation. And then as an overall efficiency measure of the economy, they would talk about the rejected energy and the useful energy way over there on the right, which was some measure of energy efficiency. And I think briefly discussing this energy efficiency thing, it provides an enormous amount of context of where we were in this moment in history and where we are today. The 1973 energy crisis that led to the creation of the Department of Energy and the Energy Information Administration was a crisis of American energy imports. About 10 to 15% of American energy at that time was imported as foreign oil. And so as they did this, there became a huge emphasis on efficiency, because in 1976, it was possible to solve the American energy crisis with efficiency measures alone. Roughly, you could say, if all cars got 15% more efficient and all homes got 15% more efficient, America would not need to import foreign fuels. That was the moment in history that we created things like the CAFE fuel standards. They are an efficiency standard. This is why we have appliance efficiency standards, because the energy problem that existed at the creation of the Department of Energy and the Energy Information Administration were largely problems of efficiency. And we'll talk about this a lot later in this talk, but we now have a challenge of energy transformation. So it's really not quite the same game as efficiency. We need to transform to completely non-carbon producing technologies, and transformation is a very different game than efficiency and includes very different language. And I think a lot of the general public's resistance to a lot of the conversation about how do you solve climate change is because we've been thinking about how to solve climate change with efficiency for 40 years, where what we need is wholesale transformation. And an efficiency conversation is a conversation about deprivation and less, which in general, maybe Europeans are a little bit better at this than Americans, but mostly throughout the world, I don't think people want to hear that they're going to have less. And I think, just as a setup and maybe revealing my punchline at the end, if we think about transformation rather than efficiency, we might find out that we can achieve decarbonisation without a whole lot of less. In fact, we might have more. This is the fabulous three-dimensional Sankey diagram. I think a two-dimensional Sankey diagram is difficult enough to understand, but this was the three-dimensional Sankey diagram that was presented to American members of Congress so that they could be well informed as they voted on measures to solve the 1970s energy crisis. I've actually seen this artifact live. It's very difficult for even somebody in the energy industry to nominally use this to write and plan energy policy. And then maybe just as a historical anecdote, energy was such a national issue in 1977 that even the Flintstones were employed in a 1-hour feature-length movie on the problem of energy And this was to do broad public education about energy issues. And I highly, highly recommend finding and watching this document because the conversation, it in some ways, it communicates to the public the energy problem better in 1977 than we do now. And it does it using cartoons, and you'll realize how little has actually changed. All of the same, so every solution that we now put on the table to solving climate change is mentioned in this cartoon by the Flintstones in 1977. So what does it look like now? This is 2015 Sankey diagram of US energy flow. America still uses quadrillion British thermal units as the absurd quantity. You can basically think about those as exajoules if that is your preferred set of units. Ultimately, I'm going to argue for the purposes of today, we don't need to think about the units, we just need to think about the proportions. This is the Lawrence Livermore National Laboratory. They do the public-facing version of these Sankeys each year, and you can look at this, and if you think back to that 1976 chart that I showed you, you can see how little both the actual data has changed and the presentation of that data. Because of my work and interest in energy, I wanted to understand, is this everything we can know? And I set about the task of looking at seeing how much more information we have and where does it come from in the creation of that diagram. Ultimately, this is a broad map of the energy data that we collect in the United States that can be used to inform how energy flows through the economy. All of these things were started in the 1970s in trying to address the two energy crises of that decade. Over on the left here, the EIA 914 and the CS 54 are actual monthly self-reporting surveys for the fossil fuel industry, where they have to report the tons of coal they ship, the cubic feet of natural gas they pump, and the barrels of oil that they produce or import. Those things are collected into the EIA MER, that's the monthly energy report. That sort of is a collation exercise. In some respects, that tells us everything we know about fossil production in the United States. There's such a focus on that. Most of the other things we know and can learn about flow here in America come from surveys. So this pink block up here, this is the Manufacturing Energy Consumption Survey. That is done every 3 or 4 years, and that is surveys that go to industry, where industry reports both the inputs of energy and the production of, what they are producing with that energy. CBEX is similarly done every 3 or 4 years. That's the Commercial Business Energy Consumption Survey. That looks at energy flow in commercial buildings. So whether you run a restaurant or a mall or an office, this pertains to what energy input goes into those buildings and where it flows. The REX is similar for residential buildings, the Residential Energy Consumption Survey, that's in orange. The TEDB is the Transportation Energy Database, and the NHTS is the National Household Transit Survey. Once again, they are semi-annual surveys of energy consumption in transportation. Also, because of the 1970s, there was a mandate to do the Federal Energy Management Program. So that very bottom blue area there is the energy flow in all government offices and departments and buildings. And finally, there's one other flow out here, GTAP. This is the Global Trade Analysis Project. This is the only data source here that's not a government collected and collated data source. It is a reasonable way to do estimations of imported energy flows to the US in terms of embodied energy in products, and we'll cover that a little bit later. Just for reference, here you can go and find and look at all of these data sources. What you can now do is once you reconcile the time stamps and the units of all of that, of all of those efforts, you can actually make this much, much more comprehensive Sankey energy flow diagram throughout the whole US economy. And so that's an exercise in very careful accounting and reading an awful lot of footnotes. So I think I might be the only person in the United States who's read the 50,000 pages of the sources of all of this data and know where it comes from. Just to give you a taste of the detail. So in transportation, these are all the vehicles by category, but you even have information about, on the right-hand side there, how much energy is used, for example, to move in trucks, class 7-8, so that's large trucks, class 3 to 6 and more sort of European-sized box trucks. And on the right there, you can see the energy content in quads of moving various products within those trucks. We also can get interesting statistics like, 0.66 quads, which is roughly 2/3 of 1% of US energy flow is people driving to school and to church. Again, there will be some slides here that are mostly for people who wish to follow up. So I'll skip over them here, but if you need to go back, this will provide some context for the slideshow. Residential and commercial buildings are divided into different categories, and you can in fact look at the amount of energy that goes into keeping the lights on in churches or in warehouses or in food sales or in hotels or in schools and universities here. So the energy that goes into schools and universities is nearly 1% of the US total energy flow. And then interestingly, for the government energy flow in the US, this does not include the embodied energy in things that the government owns, like aircraft carriers and government buildings. This is rather just the electricity and natural gas and gasoline flows to those departments. Curiously, very few, they're mostly very, very low numbers. The Postal Service, because it has a footprint everywhere, is sort of a little bit larger than the rest, but this is nearly all dominated by the Department of Defense, and in fact, which uses about 0.75%. You can actually go in more detail and look in that, and about 0.5% of US energy flow is in oil that is used for jet fuel to operate their jet fleet. Again, we have incredible details about manufacturing, right down to whether it's used to make cement, lime, paper, etc. It's useful to understand that most other countries in the world don't have data this good. They have not collected it for this long, and those countries that do collect data like this often modeled their collection systems on how the Energy Information Administration in the United States did it. And that will be important. You might be wondering why I'm showing you all this detail, but as I actually show you some of the structural errors that we baked into this data 30 or 40 years ago, it will hopefully get you to think with a little bit of skepticism about the energy data you might be using in Europe. And just, hopefully it inspires some of you to go and read all of the footnotes to make sure that some of the problems are what they are. So after you look at all of those energy flows that we officially collect, you might say, is that everything? But as it often took me 3 or 6 months after doing the original study to find that there were some things that were energy uses that didn't fall under any of the surveys or measurements that were in the official data. Street lighting is one of those things. The lighting over parking lots is one of those things. Because they're not inside buildings and they weren't inside federal buildings, they didn't fit in any other category, so we missed those. They're not huge flows, but actually wastewater treatment and municipal lighting are reasonably significant. These are 1/10 of 1% or 1/4% of US energy flow. and you can see their values there. So you also need to go back and add those. Then what the other major energy flow that is not captured in the US is the embodied energy of imports. This is estimates that you can glean from the Global Trade Analysis Project. So on the left is the source country of the primary energy source that produces products that are imported to America as net imports. So basically that green Africa, that is South African coal being used in China to make products imported to America. This orange square here, Asia, that's actually mostly Australian coal because it gets categorized under Asia. Again, being used in China to make products imported to America. I think this one at the bottom is interesting. This is Russian natural gas because Western Europe has a paucity of natural gas and it's mostly imported from Russia. That is Russian natural gas making Legos and Audis that are imported to America. So intriguingly, America is importing an estimated 10 quads of energy in imported products. Here you can go and actually follow the original sources of all this data. So this slide is there for reference. But it is interesting to contemplate that in the same way America had a 10% energy flow problem in the 1970s, which was imported foreign oil, America solved that a little bit, but it created a new problem because of the net imports problem, where it is importing a lot of foreign energy. And I am not satisfied that this is correctly accounted for in global estimates of carbon per capita, just as an interesting aside. You get geographic data in the US, so you can see every state where the natural gas, coal, and oil come from. Curiously, I think you Europeans you love jokes where Americans are the punchline, so I may as well tell you this. 88% of fossil fuels in the US are produced in the states that vote Republican. And I think that's very important to understand. I think it's 86% of coal and 88% of oil and 87% of natural gas. It turns out to be about the same for all of them. But if you would like to understand American politics through the lens of energy flows, fossil fuel flows are absolutely critical to the economies in those states today. And the reason the Democratic leading states probably don't care is because fossil fuel production has virtually no impact on their economic output. Curiously, however, the reason those states have a lot of fossil fuels is because they are large in area. So they're, Wyoming, Kentucky, Pennsylvania, Montana, Texas, these are big states. And so turns out that the same states also have the highest renewable energy resources, and Texas is finding that out with wind, others with solar. And so to switch the narrative in the United States might be convincing these states that they won't lose because they are going to lose owning American oil energy supply today. They will win because they have the most land area to produce America's energy supply in a renewables dominated world. All right, this is again all the data put back together. These are very high resolution PDFs, so you can go in and zoom around and have a look at this and find out that 0.25% of US energy is used in the commercial meat business, for example. I'll let that sort of exploration be done by you. You can also explore this at a website called departmentof.energy. But I think now I just want to say how I would now like to point out some incredible mistakes that were structurally baked in 1970 that still persist in the way we think about energy today. The 1960s and 70s saw a huge amount of hydroelectricity built in the United States. people wanted to understand, how do you put hydroelectricity as a primary energy source into our energy flow diagrams? What is the definition of primary energy for hydroelectricity? And obviously you can't use tons like you can with coal, you can't use cubic feet you can with natural gas. So what do you do? Do you use the surface area of the lake? Do you use the catchment of rain? And what was decided upon, curiously, was that they did the thought experiment, well, what happens if there is a very long extended drought and that hydroelectricity plant produces no energy? Then we would have to turn on a fossil fuel plant. So let's define the primary energy of hydroelectricity as the electricity produced at the output of that plant multiplied by the average inefficiency of the average fossil fuel plant. And so because of that, since the 70s, in all federal reporting of energy flows, we report 3 times as much primary hydroelectricity as is actually produced because of the definition of primary energy for hydro. So this means we invented as an accounting technology, technique, a couple of quads that never existed and were never produced, in order to solve this semantic definition of primary energy problem. That problem in hydroelectricity and that definition was applied to solar, it was applied to wind, it was applied to biofuels, it was applied in a slightly different way to geothermal. And so we consistently over-report today, continue to over-report in America the primary energy from renewables. I believe because the EIA, Energy Information Administration, did that in Australia, at least for a while, the IEA also followed that. And there are, I believe, mistakes in the European and global data that are structural. Why is that important? That's worth a couple of % of energy flow that doesn't even exist. It's just as an accounting thing.
I have a quick question on this one, because I do not have the technical background. What you are saying is that all these renewable energy sources appear to be a lot more inefficient than what they actually are, because there is a higher capacity of generation calculated in relation to what actually comes out in electricity produced?
It means in the official reporting, so at the end of every year, America says we use 98 quadrillion British thermal units. But 2 of those 98 quadrillion British thermal units were never produced and never existed. They were invented and come from the primary energy from hydro and the other renewables, and the definition we had for those renewables that gave them the same inefficiency as the average fossil fuel power plant. So it's a highly technical issue, but it means we over-report in the official statistics the amount of renewables that we produce. And ultimately, and you'll see as I go a little bit further in this presentation, and in nuclear it's even more pronounced, we are imagining that solving climate change is harder than it needs to be because of some semantic and definition problems that are structural problems in the data that everyone in the world that I know that does energy modeling uses. And this is because this was decided in a footnote in a DOE document in 1974, and then people forgot. So it's a little bit...
There is a follow-up question. You just said people forgot. The follow-up question is the current primary hydro still reported with this methodology, and how is it reported in the IEA? So it sounds like it's still the same.
Still the same in the EIA in the US, and I think it is still the same in the IEA. And part of what I do in giving these talks is trying to call out that and trying to improve this, because I think, I mean, it leads to an answer that it's a little bit easier to solve climate change than you think. But let me do a few more of these structural errors, because that question actually generalizes. So the question of how do you do primary energy for nuclear power was also an interesting thing. Do you use E equals mc squared or the energy density of uranium? People decided against that because in the 1970s, we were mostly only using light water breeder reactors. They only use about 1 or 2% of the energy that's contained in the fissile material. And so if you used that as the primary energy definition, it would have made an absurdly large primary energy input of nuclear, and it would have shown that nuclear is 99% inefficient in a sense, because it extracts so little energy from the fissile material. So the nuclear energy, primary energy definition is actually the amount of electricity produced and the losses in the steam cycle. So it ignores the energy content of the uranium and only focuses on the energy losses on the steam cycle on the back end of the plant. Because of this, and because those steam cycles are only about 35–40% efficient, we over-report the amount of electricity produced by nuclear and the primary energy of nuclear by a factor of more than 2 and close to 3. And so because nuclear is such a large proportion of American electricity supply, it means we over-report another couple of quads of primary energy as something we need in America. And I think that's also true in, that could also be true in Europe. And I'm sorry, I haven't, I'm not paid to do this work anyway, so I've done it for America out of interest. I would love to do it for Europe, but I just have a suspicion and some evidence that Europe just cut and pasted these definitions from America, and that the whole world isn't quite seeing the energy problem correctly because of ways we measured energy flows in the 70s and defined it. Then I'll just say there's a curious fact. When we think about electricity in these energy flow diagrams, people were very concerned with, for example, the amount of electricity used in electricity generation plants and the efficiency of those electricity generation plants. But that means we're treating fossil fuels different to electricity. And what do I mean by that? About nearly 6 quads of energy is used as inputs to petroleum refineries. What that really means is we use 3 or 4% of American energy in the form of oil to make gasoline. And so what I'm really pointing at here is there's a huge amount of energy use in the production of fossil fuels, their refining and production, and we count that as a useful energy flow in the industrial sector. We don't count that as an inefficient energy flow in the transportation sector. And given that, more than 10% of the oil we use is used to make gasoline, it really means that when an American thinks they're driving a vehicle that gets 25 miles per gallon, that vehicle's only getting 20 miles per gallon because of the oil that was used in the refining process to create fossil fuels. And because these things get defined under the industrial sector, not under the end use sector, it means that when we plan or model how to supply energy, renewable energy to the United States, for example, we think we need more, too much. So just to go through all of those things, nearly 1% of US energy flow is pumping natural gas through 4.4 million miles of natural gas pipeline. Nearly 2 quads of American energy flow is used in the oil and natural gas extraction business, 6 quads in petroleum refineries. 1/4 of 1 quad of US energy flow is using trains to get coal from the mine to the electricity plant, and coal mining takes another 1/2 quad. So 7 or 8%, or actually closer to 10% of US energy flow is being used to mine, find, and refine fossil fuels. And that'll be important in a minute. I'm going to maybe skip a couple of things. All right. So I just gave you a whole bunch of history of how we think about energy flow. I've given it to you in terms of the American experience, but America has measured these things for the longest time and wrote many of these definitions. And I have seen that a lot of those definitions were cut and pasted internationally. And so I think the whole world has some portion of these mistakes. But now we come back to it's 2019 and we're all trying to figure out how do you decarbonize. And let's use this is the American economy as an example. The approximate US energy economy today is considered to be 100 quads all the way over there on the left. So what I did in this is essentially a very high level model of the US energy ecosystem. And you can see that I've pulled out, and maybe you can see my cursor if I put it over the screen. So what I'm doing here is at every point where I can pull out some energy flow that is irrelevant in a world where we commit to decarbonization by electrification, I do so. This electrification, because I'm sure there will be questions, this electrification is agnostic to where those electrons come from. It doesn't matter if they come from solar, wind, geothermal, hydro, or nuclear. It's just, this is trying to be politically agnostic as to the electricity. It just wants to look at decarbonization. So let's look at what happens when you think about at the scale of the US economy of electrifying everything. Again, I will jump back to I'll come back to a lot of these slides. So here is those, sorry. Here are energy uses in the US economy on the right that wouldn't be needed in a world where you have electrified everything. So 16% of US energy flows on the right there is the inefficiency of making electricity with fossil fuels. So these are the thermoelectric losses in the steam cycles on coal and natural gas and nuclear plants. In purple, so the gross assumption on the energy efficiency of a fossil fuel powered car or truck in the US is they just assume that all of those vehicles are 20% efficient from well to wheel. Electric vehicles are more than 80% efficient from well to wheel. And so if you just do the thought experiment, what happens if we electrify all light vehicle and truck transportation in the US, and we do it with electric, and you use the assumption that they're 3 times more efficient, then another 13% of the energy that Americans think you won't need. You can do a similar thing around gas heating. The majority of buildings are heated in the US with gas. If you use merely the assumption that you would use heat pumps to electrify and decarbonize all of that heat at a COP of 3, another 5.5% of US energy that we think we need, we don't even need to produce. That tiny green thing is continuing to use LEDs over incandescents, but in some respects that's irrelevant. 6.5% of US energy flow we don't need, because in the decarbonized electrified world, you don't need to mine, refine, and move fossil fuels. So that disappears. Also, because of curious definitions, we include in US energy flows fossil fuels that are used that wind up in products. This is asphalt in roadways. This is oil that becomes plastics. In some respects, those are fossil fuels that don't end up having a carbon dioxide input, and they don't end up in energy. So if you're trying to figure out in just about the energy economy, you sort of fairly need to pull the fossil fuels that end up bound up in products out of the energy question. That's about 4.5% of energy flow. This semantic error, which is the definition of primary energy around hydroelectricity and nuclear, is responsible for about 8.5% of energy. So 8.5% of the energy that the United States thinks it uses today, when it is reported that we use 100 quads, it's 8.5% of energy that never existed and never was produced. This is a structural, so, just straight off the top, if you're thinking about, okay, how, it makes it 10% easier to supply America's power supply just on this semantic definition error. And then there are around about 3% of US energy flows are in basically in stockpiling and accounting methods used pertaining to petroleum, coal, and natural gas stockpiles. I see, is that a question, Antina?
We have had coming in through the chat a question. Heat pumps with, and I must admit, I don't know what the acronym stands for, minimum COP of 3. You mean only geothermal heat pump? I don't know if you know what the COP is, otherwise it would be nice.
A COP is a coefficient of performance, and could be for an air source heat pump. So when you electrify heat, if you don't wish to burn natural gas to heat the building, the best idea that humanity has is to use a heat pump. That could be a geothermal heat pump that uses the groundwater or the soil as a reference temperature, or it can be an air source heat pump that uses air as the reference temperature. We just use the conservative assumption that either one of those is used with a COP of 3, which is an existing working technology today. So this is just to say, I'm not intoning some fabulous invention that doesn't exist yet. I'm going to use off-the-shelf COPs for heat pumps that you could go and buy in Germany tomorrow. And sorry, I realize that the sun has come up here, so the contrast is terrible. There you go. Maybe that's better. So what?
You say roughly 60% of all of this, all of the energy gets lost. Oh, 58. Here it says.
Yeah, I think this is very important to emphasize, and this comes back to my conversation about efficiency. So America, since the 1970s, has had a dialogue about energy efficiency. The largest department within the Department of Energy that works on energy technologies is the EERE, Energy Efficiency and Renewable Energy Department. They appended the renewable energy bit later. It started out as the Energy Efficiency Department. So strong has been the intellectual hold of efficiency is the answer since the 1970s that it's baked into the way we think about it and are even contemplating solving the climate problem. But efficiency measures have not worked to really contain things. But what I'm really trying to argue is it's not even useful. I think energy, try not to do any stupid energy efficiency things. But what this diagram says, and this will be an uncomfortable thing to say to a European audience, is that if Americans kept their oversized cars and just made them electric, and if they kept their oversized houses and just heated them electrically, and if they just electrified the rest of the economy, they could do everything they do in America today with 60% less energy than they consume today. And so you can do all the efficiency measures you like as traditionally defined around efficiency, and you only make 5 or 10% differences to US energy flow. If you electrify the entire economy, you reduce the energy flow so enormously that it changes how you think about the achievability of decarbonizing a country like the United States. And Antina, I see you have a question.
Well, now I myself have a question. What stops them?
The same thing that stops you. It is politics that stops us everywhere in the world. I think Europeans are marginally ahead of America, which is marginally ahead of Australia. But you know, we're all planet fucking hypocrites, and if we can begin there and agree that we're more like each other than not like each other, that would be useful. If you do per capita energy flows for all the countries in the world, many of the European countries that think they're so much better than America as an average, turns out are exactly like Americans. So the Norwegians and the Swedes think that because they use on average as an electrical equivalent about 8 kilowatts per capita, Americans use about 10.4. But it's actually for the historical reason that European cities are closer together and European homes share walls in row houses. So because of the inbuilt efficiency of those two things, that accounts for the difference between per capita energy consumption between Europe and America, much more than Europeans believing that they are morally superior. So just to maybe set the record straight, I don't think anyone is winning this game. So when you ask, why isn't America doing this? I say it's the same reason Europe isn't doing this. I think it's a bit of a failure of imagination. And also, honestly, it's only in the last 5 years that renewable energy prices are, of particular electricity, are competitive enough to make this game different. Yeah.
Okay.
And
I have two more things coming in here. One question is in the 58% less energy, are the inefficiencies in an electrified economy included?
yes. So you could additionally now start doing things like insulating the buildings more, and you would reduce this further. So this argument says, before you even think of anything that is a traditional efficiency measure, all you do is electrify everything and correct the historical accounting errors. We need only 40% of the energy we used to think we need because of the inherent efficiency of electric machinery. And this ends up being important when you think about the amount of wind turbines and the surface area that we have to put solar cells on and the number of nuclear power plants that we don't wish to build. It is somewhat reassuring that we need about half the energy that we thought. You could do additional efficiency wins here by making the cars smaller. You could do additional efficiency wins here by making the cars more aerodynamic. You could do additional wins here by heavily insulating homes and doing triple glazed windows. Those would all be additional. But those savings are nowhere near as large as the win merely in a commitment to the electrification of the economy and fixing some of the... Sorry, that's an American car. A very efficient American car you can hear in the background.
Another question. Have you been able to compare forward-looking energy scenarios in terms of primary energy? It would be interesting to know how a hydrogen, methane, power to liquid, power to gas scenario compares with an electricity scenario.
So if you add hydrogen or methane, and my experience here, I actually built and sold a company. We make hydrogen and natural gas tanks for the world's clean vehicles. So I'm very aware about using compressed gases as energy sources. You pay a penalty for going into hydrogen and back again of about 20% round trip. So any portion of the economy you would like to use hydrogen as an intermittent, as a battery for, you'll pay a very high price in compression. And that's really the only way you should think about, hydrogen, methane. They are batteries, and they're not quite as good as electrical batteries in a round trip efficiency sense. What should maybe concern you more, I think hydrogen, and I think Europe is doing sensible things in terms of thinking about hydrogen for industrial heat. So high temperature industrial processes, traditionally we burn coal so that you can get 1500 degrees Celsius and higher temperatures, which is required for some things like cement and steel. The only non-hydrocarbon that we can contemplate to use to achieve those temperatures industrially is hydrogen. So I think hydrogen is very sensible in that scenario. Having worked through the economics of storing hydrogen at very high pressures inside tanks, which always end up being made out of carbon fiber, I believe that batteries are once batteries get to around under $100 per kilowatt hour, the round trip storage cost of batteries is lower than the round trip storage cost of hydrogen, purely on the cost of the materials to make the tanks for the hydrogen and their lifetime. So I believe that hydrogen is useful. It will be a niche player in the future. It can assist you in bridging the summer-winter energy divide, but it's not a terribly cheap battery. Tina?
Next question. How do you electrify? Where does the energy come from? And don't you have storage losses or grid losses? Are these included in the minus 58%?
This assumes the same historical grid and transmission losses of the US energy economy, which is 4 to 5%. Now, you might ask the question, I think that's a great question, but I'm going to take a few steps back that might get me there. And I don't know whether I have a slide that shows this better. Maybe let me just jump around to remind myself what slides I have. I may not have the slide here that you want for that question, but let's start here. So America today averages annually the electricity delivery at the rate of about 450 gigawatts. To do this scenario of a completely electrified economy, you would need to deliver somewhere between 1.5 terawatts and 2 terawatts. So 3 to 3.5 times the current delivered electricity. In a conservative estimate of the amount of that electricity you can produce on American rooftops, you can get 300 or 400 gigawatts equivalent. So our residential rooftops are good for a quarter of it. Commercial rooftops are good for another 10% of it. America has 8 parking spaces per car. They have 250 million cars. If you use some small portion of parking spaces for solar, you could produce another 25% of it. So it is completely reasonable in America, mostly because it has low population density compared to Europe, for example, to produce all of this with solar and wind, backed by a little bit of hydro, and it is achievable. You might ask your question, what about biofuels? You would have to burn every piece of biomass on the planet would need to be burnt once a year to supply humanity's 20 terawatt power consumption. So biomass doesn't scale as a complete solution. In the United States, because it has a high or low population density, large land mass, lots of agricultural production, if you took, and there's a report called the Billion-Ton Report, which was well studied by the Department of Energy. So if you took all agricultural waste, all forestry waste, all sewage, and all food waste, you could produce close to 10 quads as a biofuel. So that's about 10% of today's energy flow, or about 25% of the energy flow here. So similar in a way to the discussion we just had about hydrogen, biofuels can't scale to the whole size of the problem, but they can be very useful for the hard to decarbonize sections of the economy, such as long distance aviation, long distance trucking, oceanic transportation, and winter storage for winter heat. And the amount of just waste biomass in the US is enough to do those hard to decarbonize sections. So, you know, in the scenario I have presented you here, this is the all electric version, but it's even slightly easier than this because we will be able to use some of that, some of those biofuels to solve some of the hard problems. So remind me your question, because I wanted that as...
The question was, how do you electrify? I do think, and where does the energy come from? You've spoken about this. Don't you have storage losses or grid losses? And I will be adding to...
The grid losses are easily modeled. I think there's an obsession with decimal place precision here, but the transmission losses will be 4 to 5%. In America, in America, transmission losses aren't as much of a problem as transmission costs. So the average price of electricity in America today is 13.8 cents per kilowatt hour delivered to a consumer. The average cost of transmission is 7.8 cents. So more than half of the cost of electricity in the United States today is the transmission cost. In Australia, Mexico, and some other countries that have deregulated electricity markets and have changed building code regulations and etc. to make the installation of rooftop solar very, very low cost, you have fully financed delivered costs of electricity from rooftop solar in Australia of 6 to 7 cents a kilowatt hour. So contemplate that the cost of electricity produced at the end point of use in Australia, meaning at your home, is lower than the average cost of distribution of electricity in the United States. Rooftop solar has not finished lowering its cost curve. So I think there is now a very simple cost argument that solar will have, we will want to use as much energy as possible close to the end sources. You would also say, of the way people have historically planned energy economies, we pretty much only contemplate the supply side, the generation side. We now need to think about the end use side. And that's part of this modeling effort, is really thinking in details of the end uses. Where are all of the storage opportunities in the end uses, and where are the advantages in, for example, this transmission problem? So if you can produce a quarter to a third of your energy much, much closer to the consumer because you're on their rooftops or in the car parks near them, we eliminate a lot of those costs of the grid. The gross cost of storage, well, the efficiency cost of storage for any electricity we need to store in a battery is going to be about a 20% efficiency loss. It's the round trip efficiency, once you do the inversions and not, is about 20%. And Tina?
So I have a question. I don't know if that's the question yet. I have a question about alternative nuclear, geothermal, and heat storage to provide additional electrification and heat supply. Heat and phase storage.
I think those three questions are slightly different. So I'm going to talk about one of them that I think is enormously important, which is thermal energy storage. So one of the reasons people who think about resiliency and supply of energy in the future are very concerned in a highly electrified world about storage and the cost of storage, and the intermittency of renewables. In the United States, close to 10% of our energy use is in building heating and cooling systems. Those heating and cooling systems can easily use water as a storage medium to store cold water or hot water that can then be used for the heating. So in a renewables heavy future where you have a lot of solar or a lot of wind that's intermittent, you could easily store and load shift the entire thermal load of your building stock by 24 to 48 hours merely by using water as the storage medium at under 1 cent per kilowatt hour, cheaper than batteries will ever be, and at about a 95% round trip efficiency. In Northern Europe, where hydronic heating is preferred not only because it is more comfortable, but also because it is much more efficient, that is an enormous storage opportunity that is rarely or never modeled into high electrification scenarios and high renewable penetration scenarios. So the inherent storage capacity in the United States in an electrified vehicle fleet and in an electrified but thermally stored building stock is more than enough to compensate for solar intermittency and wind intermittency.
Next question.
Okay.
Talking about costs, have you been able to assess system costs of different scenarios, especially potential integration, storage flexibility costs with higher variable renewable shares?
So it would be possible to build you a fully functioning grid model for the US that models all of this, and we've built some infrastructure that can do all of that. I think it's a $500,000, $1 million effort to model these things at the resolution they need to be modeled. But we don't get paid to do that. So I'm going to answer this question with an intellectual model that I'll let you build in your head with me right now, which I think is almost sufficient to satisfy people's concerns about cost. And actually, maybe the best way, I do have a slide that can inform this. Here you go. I like to think now of the grand game of energy system transformation as a game of wholesale to retail energy price arbitrage. So these are US costs for one quad of energy at various different phases. So wholesale crude oil at $30 a barrel is $5 billion a quad. Wholesale gasoline at $3 a gallon at the pump is $26 billion a quad. Renewables, although this number has come down, wholesale renewables are 6 cents a kilowatt hour. That's high. My industrial solar company, we sell 20-year fixed price contracts routinely at 2.5 cents a kilowatt hour now. 6 cents a kilowatt hour is $16 billion a quad. 2 cents is, $6 or $7 billion a quad. You can see these things. Residential electricity at 12 cents a kilowatt hour is $35 billion a quad. Anyway, those numbers are there. So think about that sort of high level modeling when we think about costs. The real problem is that the costs are now workable everywhere. It's just that we don't have the full solution. So Australia, to use a developed nation example, has figured out mostly through regulation how to get rooftop solar to 6 or 7 cents a kilowatt hour. The actual wholesale cost of the solar panels is probably equivalent to 2 cents a kilowatt hour. So there are pathways, mostly regulatory. So in the US, if you install solar, it costs you closer to 25 cents a kilowatt hour because the installed cost of solar on American rooftops is $3.20 per watt. In Australia, it's $1.20. Why is it $3.20 in America? It's $3.20 because they have more permitting processes and they have inspections, and those permitting inspections is about $1 out of the $3. The cost of the sale of solar to a residential customer in the US is 67 cents per watt. Why does it cost you so much to sell someone solar in the US? And the answer is because the solar electricity they're selling you is more expensive than the grid. In Australia, the cost of selling solar to a rooftop customer is 1 cent out of that watt, which is a tiny cost, and that's because it is a no-brainer for an Australian consumer to purchase rooftop solar, because it's much, much, much cheaper than the grid. So if you could use the Australian experience in the Australian model to set the floor on local delivered solar electricity at 6 cents a kilowatt hour, and we are, I think the projected cost for battery storage in 2025 out of China is also around 6 or 7 cents a kilowatt hour. We are at an unbelievable inflection point where the cost of battery storage on site is lower than the cost of transmission and distribution of traditional utility electricity. And the cost of generation of solar on your rooftop is close to the wholesale cost of electricity. So those prices, that saves you a lot. If you think about this gasoline at the pump at $3 a gallon, that's $26 billion. And remember that American gasoline is much cheaper than European or Australian. So in Australia, it's about $50 billion a quad. So if you can produce your solar at 6 cents and you're an Australian consumer, it's about a third the cost of filling your car with an equivalent quad of gasoline. And that's before you even account for the 3 times efficiency of the vehicle. So doing that math roughly in your head, buying gasoline to drive a Tesla-sized gas-powered car in Australia costs you 60 cents a kilowatt hour. If you can produce electricity on your roof at 6 cents a kilowatt hour, it makes sense for you not to use gasoline cars. But like I said, the future is not well distributed. Australia has fucked this up because they consider electric cars in the luxury car category. So they have a 200% tariff on imports on electric vehicles, which makes the electric vehicles too expensive. So if you could take Australian model and costs for solar, you could take German model and costs for heat pump driven hydronic heat, and you could take California costs for electric vehicles. You actually have a model of the future where you've now got 2 giant storage opportunities for that home in the vehicle and in the thermal systems of the house, and you've given them sort of wholesale energy prices. If you model that out fully for an Australian family, if you could finance that package at an interest rate of 4 to 5%, you would save the average Australian family $2,000 a year on all of their energy costs, and you would decarbonize them completely with those 3 purchase decisions. That would, by the way, work in Spain tomorrow. It would work in Portugal yesterday. Greece is already there. So you now can look at any country. You need to know a few things. What is the cost I can get rooftop solar to? What are the costs of electric vehicles? What is the retail cost of natural gas to the home? What is the retail cost of electricity? And you just play price arbitrage, and you can tell today which countries these economics work.
I have one last question. I would also want to point out we have 8 minutes left. So if anyone else still has questions, please ask them now. Saul, if you say, I need 3 minutes to close or 5, let me know. Otherwise, I will ask my question.
Okay.
That was also something that came in actually before we started. What will all of this mean with regards to grid infrastructure and needing new grid infrastructure? And what I would like to add to this question is, you've been just talking about, if I put PV on my house and storage in the basement, then it's all significantly cheaper than new transmission. Are you proposing an increasing amount of off-grid solutions? In your thinking, do you encompass the question of some grid infrastructure? We will definitely need also additional grid infrastructure. Who is going to pay for this if more and more people go off-grid? Or do you say, well, this is another level of topic that I'm not looking into. Do you have any thoughts to share on this?
I think this is a fabulous question, and it's sad that we only have 8 more minutes, but this question is perfect. So there's no way you can, although I've said a lot of words that may think you think I'm a crazy hippie who wants everyone to do 100% distributed renewables, that doesn't work, and that doesn't work in any universe. If you look at the American example that we talked about with full electrification of everything and all of those efficiency wins, you still can't produce enough electricity on the rooftops and in the car parks to satisfy. And you particularly, while you can do it in Texas or California, you definitely can't do it in Chicago or New York City. And Europe looks more like Chicago and New York City than it looks like Texas and Los Angeles. If you do a cartoon models in your head with this sort of understanding of the energy system for America, there's no way that the existing grid gets smaller. Today, the existing grid delivers close to 0.5 terawatt. Probably, if you're committed to the model that I've sort of discussed here, 1/4 to 0.5 terawatt will be locally produced with solar. Another 1/4 to 1/2 will be produced with more local-ish community solar and wind, and then the existing grid will have to grow from 0.5 terawatt closer to 1 terawatt to satisfy all of the energy demands. So in the United States, we have a polarized debate where the utilities are digging in because they're scared of this new model taking energy income away from their grid. But in reality, we need more of both if you are to fully decarbonize. And so we need to get away from the binary thinking and the fear that utilities have of their revenues shrinking and the size of their network shrinking. You need those networks to increase in size. We also need to do as much behind the meter and on rooftop energy production as possible, because that will produce the lowest energy costs for the consumers globally. So I'm really saying yes and, but I'm often, people often put you in one camp or the other. The reality is, if you look at these and you build simple models in your head, the lowest total net energy cost to consumers will be with as much as possible produced as close as possible to the end use, as much storage as possible done as close as possible to the end use. But even those things require a grid so that neighbors can share, and we will need all neighbors to share, mostly the storage opportunities. And so I think what I'm really saying, and maybe the way to glue that together, is again, if we're thinking about the blind spots of how we're trying to solve climate change and its energy problem, we're still thinking it with the 1970s frame set. In the 1970s, infrastructure was roads, bridges, dams, and transmission lines. And I still think most grid planners and energy planners think that this is how infrastructure is built. We think about giant centralized generation plants, and we think about the transmission lines, etc. But if you imagine the 21st century infrastructure includes the demand side, the use side of energy equation, as well as the supply side, then all of our electric cars are in fact part of the public infrastructure. Our heat pumps, the solar on our roofs, our parking lots, these should really be considered as part of the larger energy infrastructure, because our cars and our homes will be the largest and cheapest storage opportunity in a highly electrified and decarbonized world. So if we think about them as infrastructure, we can then think about financing those behind the meter assets with infrastructure quality financing. Today, we finance cars and heating systems of homes at retail interest rates of 7, 8, 9, 10%. We finance grid infrastructure with government-backed measures at 1 or 2 or 3% interest rates. The if you were financing these behind the meter solutions with infrastructure interest rates, everyone's energy costs would go down tomorrow. That's a fairly nuanced point that really is hard to get across in under 8 minutes. But, you know, I think we have, and this is why I began with a long missive on the history of how we have thought about energy, how we collect the data, and how we have conceived of energy solutions. We need to change that thinking very quickly, because we are still trying to solve our climate problem with efficiency, whereas that you can't efficiency your way to zero carbon. You have to do transformation. And we need to expand the definition of infrastructure so we can fully utilize behind the meter assets. The reason European utilities and American utilities and Australian utilities and all the utilities of the world are belligerent and say we can't provide you with reliable energy is because they don't think of behind the meter storage assets when they're doing their modeling. And so they can say with conviction, no, it won't work, because they have a complete failure of imagination based in backwards 1970s conceptions of what infrastructure is and how energy systems are built. Ta-da!
I take this was the end fanfare. I believe we have no open questions. I have certainly a full head by now. This was super interesting. We also received a comment on our invitation from someone who said, we've known all of this for 10 years, and I think you would agree to the statement that the knowledge of these things is not yesterday's discovery, but we've been knowing this for a while, but we still haven't really learned to act upon this knowledge politically. So
well, I think it's incorrect to say we've known this for a while. I think there are around about 100 people globally who have actually read enough and understand the history of how we've collected and thought of these things. But we haven't communicated effectively, as evidenced by the fact that we still don't report energy data correctly nationally or globally in any country. A lot of these errors and artifacts are still in the way we do the reporting. So I think probably who wrote that comment is right. They've probably done their homework and they've known it, but I've known it too for more than a decade. But I'm still having to repeat it all the time so that it becomes acknowledged and understood at the political level such that we can move the needle. I think these last comments on infrastructure, a tiny number of people have understood that for 10 years, but I am advising multiple presidential candidates. I'm still doing high school physics tutorials with them, with American politicians and European politicians and Australian politicians on this stuff. So I think, no, a few experts have known this, but those experts have failed to communicate. And the reason the conversation is broken globally is a little bit on us, because we have not strongly enough educated the important players as to the possibilities and the intellectual mistakes about how we think about the problem.
Very good. I can fully agree with you on this one. Hence, it's great that you've been giving us for 1.5 hours some words and charts that can help to understand and better explain the story. We've had the question, will we be sharing these slides? Yes, we will. The entire thing has been recorded, actually. So for those of you who say, I want to listen to this again, you can do it. You can also pass it on to other people. It will be on our website within a few days, I assume, the latest.
And I'm fairly easy to find on the internet, and if you figure out my email address, I will answer your questions.
That's great. Thanks a lot to all of you for taking the time. The majority of us comes to the end of the working day now. You are just getting started. Extra thanks again for making such an early morning for us. It was a great honor and pleasure.
Thank you very much.
Have a good day. Bye-bye.